thank you very much for inviting me here today. So this was a project we undertook with funding from RSSB, but had stakeholders also from Network Rail and other providers of certain type of rail products as well. But I'll be going through and doing a brief overview of what we did. Well, I say brief, it's still half an hour, 40 minutes, but all the extra information, if it's needed, is on the RSSB page for T122 using Spark if anyone needs or wants to see more. So I'll start off with, so I assume most people here are fairly familiar with track circuits, but just to very briefly go through what exactly we're interested in. So a train is detected if it's able to shunt an electric current across the wheel set here. But obviously, if you have some insulating material between the wheels and the rail, it means you essentially lose train detection at that point. So these contaminants are obviously electrically insulating. So that's what we're trying to focus on, trying to characterize what these materials are, what they do, how they're affected by certain conditions, which I'll go through in a bit more detail in a bit. So again, very brief look at what we actually did. So first of all, we analysed some data sets, so the national wrong side track circuit failure data for, I think it was 10 years from 2012 to 2022. So I look at all those incidents. And then we did some lab testing. Then we went on to track testing as well. And then we produced some documents off the back of this, which I'll briefly just introduce to you. But again, everything is online through the RSSB from the T122 project. So to begin with, the analysis of data sets. So as I said, it's 10 years, all the national data that we could get our hands on, which I think equated to about 6,000 incidents, and these are all showing clear when occupied. So essentially, you've lost train detection in these cases. But we also had an initial look at what type of track circuits were about the network itself. So we've got a very brief overview here of different routes, and if they've got a DC track circuit, which is direct current, AC, alternating current, then there's AF, audio frequency, so essentially how the frequency changes over the length of a rail and whether it changes with a train going over it. An impulse, which are high voltage impulses, as the name suggests. But clearly we get a lot of DC track circuits still knocking about, the vast majority. And then we also get a sizable number of each of these spread across the network and all varying depending on the region. So to start off with what we actually found from a brief overview from the national data analysis. So first of all, this graph here, the bigger the circle, the more incidents apportioned to it. So for example, you see here, this big orange circle is all the leaf incidents that happened, and it's that much bigger than all the rust incidents. And the circles inside, so you've got all the DC leaf incidents, then all the DC leaf incidents happening in November, so this purple circle. So as you can see, perhaps unsurprisingly, leaves dominated, and especially in autumn and on DC track circuits was the big cause of wrong side track circuit failure. There's also quite a lot of rust incidents, but these, as you can see, also on DC, but spread out throughout the year, so didn't peak in November and October. And sand seems to make a rising contribution as well, but this one mostly in autumn, with grease and oil making a much smaller percentage. Let's look how these contaminants were shared out. So, as I said, about 6,500 instances are what we looked at. About 20% of these were other, so some sort of a technical failure elsewhere, which wasn't attributed to railhead contamination. But you can see about 60% of all of this was leaf contamination only. So we looked at the breakdown of these incidents by route. So you can see predominantly it fits for national data. So for example, Anglia has predominantly leaf incidents with some rust and sand as well attributed. But there were a few outliers such as Wales and Western region where you've got actually more rust instance and fewer leaves instance. We also then had a look at how this varied year on year. As you can probably see, it fluctuated wildly. There didn't seem to be much of a pattern. I mean, there's multiple reasons why it might change from year to year, such as reporting, rolling stock, etc. And also just this 2022 data is only partial because we started this data analysis, I think, at the end of October is when the cut-off for all the data was. Breaking it down by month, again, we see what we saw before, large spikes in October and November for leaves and for sand to a lesser extent. Then this rust throughout the year, but it does seem to drop off a little bit at the height of the summer. And the grease and oil attributed incidents were low throughout the year. We then had a look at how it broke down by a day of the week. So from this data, one limitation we had is we couldn't get the time, only the day it occurred on. So that's how granular the data was. This is as close as we can look at it. So leaf and rust seems to be much higher on Mondays for the national data, whereas something like sand seems a lot steadier throughout the week. We saw a similar pattern to this in most regions, though I've included a list here of the exceptions to that, where Monday was not the biggest day for wrong-side track circuit failures. So now we looked at time. Now this is just a brief overview of the track circuit types that was occurring on. So obviously we saw the most wrong-siders on DC track circuits, but we also have the highest, more DC track circuits than AC track circuits. So this graph here is an attempt to normalize this relationship. So you can see here, even when normalized, DC track circuits still contribute the highest proportion of wrong-siders, with AC producing about proportional to what it is, and then audio frequency and impulse track circuits both producing much lower. So essentially this shows DC is actually the worst. It's not just the most numerous track circuit. We then had a look at how many incidents a track circuit would see. So this is one particular track circuit. So the majority of them never saw a wrong-sider in the 10 years that we had data for. So that's about 93%. So we haven't included it on here because it's just so skewed off. It's up here somewhere past that. And the majority of wrong-siders that did see it, majority of tracks that did see a wrong side only saw one or two. So these bars here. So they saw 1 in 10 years. And very, very few saw greater than 5 incidents. So that's an incident every 2 years, for example. So it's almost vanishing off at this point here. Then we found also, looked at the individual track circuits, saw which ones were producing the most. So you can see the track circuit with the most wrong-siders was this one. It beat Bedford and Bletchley with 21. So these high locations were mostly due to leaf contamination we saw, rather than a particular area with a lot of sand or a lot of rust contamination creating these wrong-siders. So we then decided to look at the track circuits in a bit more detail by trying to ascertain whether there was some relationship between length. Ultimately, we didn't have detailed enough track circuit data to normalize this, but we did see that about 10% of all the wrong sizes occurred on track circuits shorter than 20 yards. So these level crossings, junctions, etc. And there does seem to be some sort of trends between length and number of wrong-siders, but obviously without normalizing the data, this is just an observation at the moment. And lastly, so obviously a wrong side is a function of the rail, but also the wheel itself. So we decided to have a look at traffic and see what impact there was there. So we saw about 8% of them, they didn't come as standard, included head code data, but nothing more granular than that. So that's where we can get up to. So we can say, for example, the majority of cases where passenger trains of some variety is with head codes 1 and 2, and freight much lower at the moment. So after doing that national data analysis, we ascertained that stuff like leaves, rust, sand were contributors to wrong-siders. So we wanted to look at these more closely in the lab. So we've got a high pressure torsion system at the university. So we've used this before for testing friction in the wheel rail contact, where we can apply little third body layers and basically apply normal pressure so that it's similar to that of an actual wheel rail contact. So I think 900 megapascals, something like that, and then twist it through. So we set up a circuit around this to see whether what these contaminants were doing within the contact. So we had a look at both DC and AC power supplies. So because the data is more clear with the AC, that's all I'm presenting to you today. But again, in further reports around DC stuff, if anyone's interested. Then we looked at the range of contact pressures. So in megapascals, it may not mean as much, but these are approximately equivalent to 8-ton, 12-ton, and 20-ton axle loads. So going from very light rail to freight, essentially. And then we looked at leaf rust and sand. We also did some tests on roughened surfaces to see what difference that would make, though these were smaller in number. So to show you what these actually look like, so this was our leaf layer after conditioning it. So we got more leaves in actuality when we did these tests. These were mostly from tests looking at friction, whereas for the tests involving isolation, we wanted a lot more leaf layer. But you can see we can create an actual black leaf layer within this rig. We also then looked at sand, so placing it like this, so what should roughly be representative of a maximum amount you can get in there using current sanding stuff. And then rust, we quite literally just left them outside, so to create that layer there. So I'll very briefly go through these. So essentially this graph here shows a clean contact and shows the range of AC voltages you're getting across there. So the AC cycles from +2 to -2. So it goes through 0 volts. So you will always get some voltage measurements at 0 volts from this histogram, and then some at this point here. So it goes up to about 0.1. So this is indicative of a clean contact. So it's perfectly conductive, essentially. Whereas when we introduce leaves into it, you can see from this here, it goes up to 1 volt all of a sudden. So this little peak here still cycles down to 0 volts because we're still cycling from +2 to -2. But this graph here is indicative of complete isolation between the wheel and rail specimen. So the actual thing to take away from this is that these 4 here show complete isolation between the wheel and rail specimens, and these were at 600 and 900 megapascals. Whereas once we increase the contact pressure even more, we'll start to see this breakdown to something like a clean contact as the test went on. So essentially, these leaves and their ability to electrically insulate were dependent on the loads that were being applied, both normal, as in what we're putting directly on top of it, and tangential. So how when we were sweeping through the contact, it would break down as well. And similarly for roughened surfaces, so these are at 900 megapascals, where previously we saw complete isolation. Now we're seeing it breaking down to something being fairly conductive. So we did see the effect of roughening the surface did make quite a big impact on the electrical conductivity of it. We also, as I said, looked at sand. So this was a bit more clear cut. You can see it, these 900, 1200 megapascals, so 12 and 20-ton axle loads roughly. We see almost complete conductivity in the contact. Whereas at these lower loads, we see it not being quite as clear, and we're seeing more electrical isolation up to this point. So when we looked at these in more detail, we found that after a certain threshold pressure, the sand would tend to break down and create complete conductivity in the contact. So I think this was about 750 megapascals for some sort of idea. So about 10 tons of axle load, we saw the sand break down and no longer electrically insulate. Lastly, we also looked at rust. Rust essentially went away as soon as we applied any real loads. This might have just been how we made it over time. It wasn't the thickest in the world, but we did see some sort of electrical isolation from it before full loads were applied. So again, the headline is very dependent on the load you're applying, whether rust is electrically insulating or not. So from those tests, we then went on to do track trials as well. So this is a bit different as we used a low voltage DC track circuit at Wensleydale Railway. So this was made from actual track circuit parts. So some of it we got from Network Rail, etc. And it's all representative of an actual track circuit that you would see in the wild, essentially. So this track circuit down here just shows the makeup of it all. So we're able to test what we were sending out onto the rail, or measure what we're sending out to the rail, and what we were getting at the other end, basically, and see what effect the contaminants were having on it. So for these tests, we used a class 142, so a pacer for all our tests. And to just briefly, this will help explain the graphs that I'm about to show. So we apply the contaminant in 2 patches, like this diagram down here. So essentially, as the train entered, because each carriage has 2 wheel sets, there's no bogies on the pacer, just to make this clear. So entered into a track circuit past this insulating end post. It went onto the first contact patch, and you can see the effect of the contaminant. The first wheel goes back onto steel until it gets onto a second contact patch, at which point the second wheel entering the contact area will get the rest of this first contact patch. So essentially, we'd see 2 points where the wheels were completely physically separated from the rail. And lastly, just to show you what we were creating. So we weren't able to create rust from these in these tests, but we were able to make a leaf layer up here, and we also applied sand via the sander as well down here at the 2 kilograms per minute. One thing to note, a pace is a bit different to a normal train, that it sands from the leading wheel set, whereas for a normal train you'll have a few wheels before you start sanding. So that's why some of these results are a bit different to what we'd see in the real world. And lastly, down here we looked at leaf and sand at the same time down here. So just to explain these graphs a bit, so outside of a track circuit, getting a voltage going from one end to the other and essentially not energizing the signal that you'd have at the end, so it's showing unoccupied. And then when the train enters, this will drop down, it'll shunt short, and it'll energize the relay at the other end here. So these tests are showing it as a DC signal, either almost binary in some ways, but in reality we had to remove a 50 hertz cycle that was left over from the filtering that was done before sending out onto a rail, which I believe, we'll talk about very briefly here. So in reality, what I showed you is just a filtering. In reality, when we say this is a DC track circuit, because we're powering this from the mains, we're in reality, when you look at it in enough detail, we're looking at an AC or a rectified AC circuit. So we're seeing essentially these, the negative value should be removed, or flipped around. So you should see it go up like this, but you were still seeing this negative value down here. So we found from looking at a model that we created that this was due to the relay coil. So essentially what gets energized from the other end. So this inductance in a relay coil proved very important as well for when we were applying our contaminants. So to first of all look at the leaf results. So this is fairly clear what happened. As we're going down, the train initially enters, rolls onto this leaf contact patch, and we're getting a spike in voltage here. And then it rolls onto the next contact patch, and we're getting the second smaller spike. So this first rollover seems very standard. It goes up to about 0.5 volts, which is enough to electrically insulate the train, meaning it's losing train detection here. And then this second pass, so this bottom one here, so this is the first pass, this is the second pass, we'll see a lot more variation of behaviour, but we're still seeing that the leaves are having an effect even when the train's coming back over the leaf contamination. So to show you what this looks like in detail, it looks like a fairly standard waveform, so but with some noise in there as well. So it almost looks like there's no train present, basically. Right, so compare this to sand. So from the sand, we saw a huge rise in voltage from this first pass, here and here. Whereas on the second pass, we saw it much less persistent. So we found that the sand was causing a large increase initially. Then when it rolled back over, it was all getting essentially brushed aside. So it wasn't a long-term problem. It was only for the wheel sets which were being sanded. And to show you, this looks quite different to what we saw previously for leaves. So you can see here we're creating these huge voltage spikes as it's going over the sand. So what is essentially happening is the sand is, as it's rolling over a particle of sand, the sand suddenly insulates, so it interrupts it. So these sudden interruptions create an on-off behaviour that means the inductance in the relay coil creates large voltages, increases in the voltage, higher than even what we're feeding into here. So we're seeing the effect of sand and the inductance coil and how they interact with each other. And lastly, we looked at leaf and sand together. So you can see we're getting the high voltages in the initial first pass, but we're getting this persistency in the second pass as well. So what's essentially happening is as the sand and leaves go together, we're getting the worst of both worlds. So we're getting the high voltage increases from sand coupled with the persistency of leaves, so it's not cooling away from a railhead as it was with just sand being applied. And lastly, you can see the AC waveform is a mix of what we saw before. These are voltage spikes, but with more of a sinusoidal look to it. So we also had the chance for these tests to look at the drone images. So these were taken at above 50 meters, which is the minimum operating height that's allowed for overhead lines at the moment. So you can see this was taken from a test where a lot of the leaves were removed when we were trying to get down the methodology for putting it down. So we don't see a lot, but we can see little bits of leaf on the railhead already. So this proved quite promising. It seems like from drone images, so no men on the track itself, we can actually ascertain whether there's contamination on the railhead itself. So that was all our lab and field testing. We next then had a look at some case study lines. So we picked 6 case study lines and looked at them in more detail, all the data analysis that we could do, and taking the lab results we had as well to feed into it. So to briefly show you, these are 2 of the 6. So this is Bedford Bletchley, which had a lot of wrong-siders a couple of years ago, and whole line. So you can see each of these little lines here represents a track circuit which has been subject to a wrong-sider. So it shows the date it occurred on, the mile marker along the line it occurred on, and the type of contamination that was attributed to it. So you can see Bedford to Bletchley in autumn of 2021 had a lot of leaf incidents about here on the line. So what we essentially thought was these horizontal clustering, such as here, could be attributed to either a type of vehicle that's coming over. So if it's got a vehicle with contaminated wheel sets, you'd see lots of failed track circuits in a row, or obviously a particularly bad weather event which struck one day. Whereas something like this vertical clustering, which I'll show you with another example here. So this is the Settle and Carlisle line. So we're seeing these persistent vertical lines here. So they're always happening in the same location, basically every year, every autumn. So we can ascertain from that there's something at the site itself which is creating these issues. So in the case of Settle and Carlisle, I think it's very leafy at these two little bits here. Yeah, so I think Rob mentioned earlier that a lot of lines now have remote condition monitoring on them. So when we looked at a case study of one particular wrong sider occurring, we looked at the RCM traces from the initial train where there were no issues, and then the next train came on, and you're seeing a bit very similar to what we saw on the field tests, this little rise here along different track circuits themselves, which these different colours represent. And then the next train comes along and it breaks down even more to the point where train detection is completely lost. So from this, we can sort of see that there's an opportunity to detect wrong siders here before they become a problem here, in which we fed into our reports at the end as well. So lastly, knowing what we knew about what caused the wrong sider, the contamination, the load from the labs, the type of track circuit itself from both the field testing and our analysis, we wanted to try and get an idea of how we could parameterize or measure risk of a wrong sider occurring at a section of track. So we looked at the 6 different case study lines and tried to measure these parameters. So the traffic, so the type, so how light or heavy the axle load is, the frequency of it, and also the mix. The track circuits itself, whether a lot of DC track circuits were in use, railhead treatment trains, so how often they were being used, and this tree proximity, which is essentially how much this tree overhangs over the rail line here. So we did find some evidence to suggest that the closer a tree was to overhanging, the more chance you'd get these wrong siders occurring. So this is it all tabulated for the 6 different lines we looked at. So looking very briefly, we're seeing quite a different mix between these lines. So we're seeing some like NAJ2, which is Neasden down in Chiltern, which has a lot of trains per day, whereas something like Settle and Carlisle, where they're a bit more they're a bit sparer. Whereas something like wheel load, a lot of variation as well. Whereas something like tree encroachment, so how much it encroached onto the rail, we're seeing all that fairly high, so close to a metre in all cases, and only in Hull we're seeing under a metre. But from looking at this, we could see some links, but there's no obviously one parameter which linked to wrong siders from this. So we decided to look at this graphically. So these radar charts essentially show the bigger this is here, the more higher chance of a wrong sider. So that's why we've got 1 over wheel load, for example, here. So you can see all of them have at least some parameter which is quite high. It's not that surprising as we chose these case study lines, as they had a lot of wrong siders initially. So it's sort of confirming why they had them. And some lines had particularly large values for some things, such as tree encroachment here, whereas nothing else was particularly high for NAJ2. Then we look at BBM, which had the highest number of wrong siders, and also it's high in almost every metric apart from the frequency of railhead treatment trains that are occurring. So I think the thing we can look at this is a line that's particularly high on any one metric could be vulnerable. So for example, tree encroachment, track circuit vulnerability, but lines with multiple parameters which are high could be very high risk, such as BBM or this KWS here. lastly, from these case study lines, we had a more detailed look at rolling stock. So from before, we had the national wrong side data. So we saw from that most wrong sides were attributed to passenger trains. From the case study traffic, we were able to get an idea of how much of traffic is normally made up by passenger trains, and could see where the discrepancy between these two were and whether there was any outliers. So we saw the passenger trains were creating about the number of wrong sides you'd expect, whereas something like these light locomotives or this empty coaching stock here would create a much higher percentage of wrong siders than you'd expect looking at the traffic. Whereas the opposite was true for freight, where it was quite low in terms of the wrong sides that were occurring on it and much lower than the traffic that we saw. So this sort of reinforces probably some link between train weight and wrong siders. But again, there's multiple other things this could be showing. For example, the empty coaching stock may run earlier in the morning when leaf fall is going to be worse. So it's not definitive based off this alone. So to conclude what I've actually talked about and give you the salient points. So DC track circuits with leaf contamination in autumn produce the highest amount of wrong siders. I think that's the big take home and probably something that everyone knew or very least suspected anyway. So the electrical characteristics of the contaminants and all the ones we looked at were very dependent on the contact pressure that was being applied. So the axle load and what was happening upon them. During the track trials, we characterised that leaves had a steady increase in measured voltage, but were quite hard to remove. I mean, especially after a test, we were having to really scrape away to get it off. Whereas the sand was much more erratic, but came away easily. It was practically gone by the time we did a test. We could wipe it away, and it was still on there. Whereas when we combined sand and leaves, we got the worst of both worlds. So something which produced high voltages, but was very hard to remove as well. We also able to verify that drones were able to capture images of relic contamination in the good light that we did it in. We also saw the inductance in a relay cord that was identified as a key component. So essentially, how your track circuit is made up matters a lot beyond just what sort of voltage you're sending down there. And we looked at some risk factors to identify potential wrong side areas or traffic. So hopefully we can use this in future to try and create some sort of way of assessing whether lines may have future issues if certain factors are changed. For example, if traffic goes down, if RHT schedules change, if trees get worse and worse, with vegetation overhanging. So as I said before, we produced other documents, so this is just briefly a quick look. So we produced a document recommending points of action for mitigating against wrong side track circuit failures, and as well what to do following a wrong side track circuit failure. So all these reports and all the real detail is online on RSSB's page. That's all I've got to talk about today. Thank you very much for listening. If you've got any questions, I'd be happy to take them now. I'll just come back onto this.
Thanks, Will. That's really interesting. Has anybody got any questions? There's nothing in the chat yet. I'll start the ball rolling. In terms of vegetation encroachment, how did you measure that, or would you use data that NetworkRail provided?
Yeah, we did measure it. We measured it from satellite imagery, so literally what we could get off Google Earth we used. So we tried to, in fact, I'll just try and show you the slide here. Where is it? Here it is. Yeah, so we defined it as the amount that so we were able to create this little thing in Google Earth where we measured how much the tree was overhanging, then basically take that away from a rough area of this bounding box here to get an idea of tree encroachment. So it was all satellite imagery.
Right, that's interesting. Thank you. Mike Windsor, you've got your hand up.
Yeah, thanks for your presentation, Will. Just to give you an idea of who I am, I'm currently the intelligent infrastructure project manager for the Northwest. and I've been involved with the autumn team in the area, looking at some monitoring, etc., that we've been putting on track circuits. And I was the signal maintenance engineer for Manchester for quite some time, and we've been suffering in a particular area from wrong side track circuit failures. So quite a lot of what you've said has confirmed what we've thought for quite some time with our analysis when we've been looking at it. So that's nice to see. One thing that I would like to ask is, has anybody looked at what happens when we get mixtures of either the leaf ball, sand, any type of traction gel, or anything else that's applied to the rail, and what chemical compounds they create when under pressure? Because we have had some feedback from some of the teams that when they're applying traction gels to the rail, that they believe that it's increasing the problem. So we're wondering whether there's something in that, and we don't know whether any analysis has been done on that, because where obviously you've got several things being applied to the rail, then they're being put under pressure, which I would imagine is creating heat as well. Has anybody done any chemical analysis on any railhead conditions and what that means for the track circuit?
I suppose the short answer is a lot's being done, but like a lot of this, it's been done for adhesion. So in terms of wrong siders, there's less to look at with that, especially in terms of mixture. I mean, in terms of the national data, it's not even a category. You can't have mixtures of things when they're reporting. It's either leaves, sand, or some other. So we can't get it from the national data currently. That's one of the recommendations we had, actually, to start trying to factor that in as well. But there is been look at other types, so friction modifiers were one of them. So I think, unfortunately, the research I'm thinking of is embargoed, so it's not publicly available, which doesn't really help you, I'm afraid. But no, it's a short answer. It's not being looked at in a lot of detail, especially the chemical composition with regards to wrong siders.
Yeah, it's just interesting it would be interesting to know whether we're actually creating a compound on the top of the railhead, which is an insulant.
I mean, yeah, quite possibly is my short answer, but I couldn't tell you more than that at the moment.
Thanks, Will.
There is a national group, Mike, the adhesion research group. It might be worth us taking that question to them. Because if there isn't,
I think it is, Rob.
Done,
we've had some really good stuff in Manchester just recently. I've had some monitoring put on some track circuits which were causing us an issue over the autumn, and we literally had a very good kind of telltale on it, where the rail had been ground the night before, and within 2 trains we got an alarm on the intelligent infrastructure. We sent out staff to site, and we'd seen very serious contamination on the railhead. And you're talking within 2 hours.
One thing to add on that, we've done a lot of this for adhesion, but we have found that iron is the thing which binds it together and really creates that leaf layer. So even when we were doing these track tests, we weren't getting particularly good leaf bonding until we started using a little sanding star attached to a drill head to roughen the rail at the forehand. And then we saw the leaves were much better at adhering to the railhead. So there's definitely something in that. And again, there's proof in terms of adhesion, there's quite a bit of that. But in terms of wrong siders, there's not a lot of it, but you assume they're going to be very linked when it comes to leaves.
Thanks, Will. The adhesion research group can sometimes guide some of the research, so we might be able to provoke something, someone to look at that. Have we got any other questions?
I just chucked one into the chat there. I was just wondering if the species of the leaf makes a difference.
Hold on, I'll stop sharing here. Again, there's some evidence for this from adhesion, but not really from wrong-siders. From adhesion, we've seen that basically it doesn't, especially once you've got it into the contact. So it might matter in terms of how the leaf falls or something like that. But once the leaf's in the contact, it doesn't matter what particular type of leaf it is. And for adhesion, though, I would add. So for wrong-siders, there's nothing definitive.
It's Mike again, Will. Has there been anything done regarding wheel profiles? There was some documentation that I was sent regarding Class 66s, which were potentially causing more issues down to the wheel profile against the rail profile.
But in terms of this, what we've looked at is contact pressure, which is a function of the contact area. So it's sort of included in that, but it's not completely is. So I think for Class 66, it was partly, correct me if I'm wrong, the bogey as well, because it was moving about and going onto new contact patches.
That's correct, yeah.
So what we have also looked at, so one of the things I sort of glossed over during our presentation, we looked at the case study lines to look at the mix of traffic. So where we sort of seem to suggest is if you have a lot of different types of traffic running along a line, you're less likely to see wrong-siders. Versus if you see, let's say you've got loads of Class 158s going along, then you have a Class 66 or something that's out of scope, if you like, for what's normally on there, you're more likely to see that rise of wrong-siders. At least that's what our case study suggested.
Yeah, that's some interesting stuff then, Will. Thanks for that.
Yeah. I'll put something in the chat. This is a paper that we very recently did. Again, it's more about adhesion, but it sort of covers some of the leaf bonding in the chemical analysis we looked at. I'm not sure if it's open access or not, but hopefully that'll be useful for some people in here. I think it answers a few questions that have come up just now.
Thanks, Will. Do you have any more questions? Can't see anything in the chat. Nope. Okay then, thank you. Sarah, I don't think there's any more notices we need to mention, is there? She gone. Well, in that case then, we'll wrap up. The next meeting will be obviously in March. I think it's the 14th off the top of my head. Let me just check my calendar. It's actually me doing the presentation on the management of extreme weather. March. Yeah, the 14th of March. So if we could just thank Will in the usual manner for his presentation. It's been an applause. Thank you. And then we'll wrap up. For having me. Yeah, thanks. Oh, hang on, we've got a hand. Sorry, who's that? Just put the hand up. Oh,
no, sorry, that was me. I took it down again.
Great. Well, thank you all. Thanks for dialing in, and I hope you found it interesting. Thank you. Bye.
Bye.